I'm going to do my work up here while you do your work at your desk. So if you want to follow along, go for it. If you want to check, do it to it. Okay. Da, 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 da. Don't be this child. Don't be that child, okay? Please don't be that child. Don't be this sea-hilled. Don't be this chilled. Is it cold in here? Okay, let's see here. Take x to the fourth. Take out an 8. Give me a 1 over this. This would be 1 minus what? X over 8. X over 8. Negative x over 8. I want a minus there, so I have to take a minus and negative. So we're going to take out an alternator, right? Because I see that negative 1. You'll see what I mean in a second. N equals, not goes to, n equals 0 to infinity of x to the fourth over 8 times negative x over 8 to the n, which would be equivalent to n equals 0 to infinity of negative 1 to the n, taking care of my alternator. I have an x to the fourth, and I have an x to the n. On the bottom, I have an 8 to the first and an 8 to the n. Let's clean that up. Now, if you're already to the next step where I'm at, and you skip this middle step, that's totally fine. I got an alternator, negative 1 to the n, x to what power? 4 plus n, or n plus 4. I like the variable first. All over 8 to the n plus 1. There is your power series representation. Okay, so now today, what I want to do, and I might go off the cuff here a little bit and just kind of, I'm going to pause this so I can get the. All right, so we're all in agreement, right, that if I did this, this is what we conversed about yesterday. If I went out, let's say 5 terms, I'd have 1 plus x squared plus x cubed plus x to the fourth, and on forever. Everybody good with that? The first term in this series would be 1, and the common ratio would be x, right? When we talk about geometric series, which this is one of them, right? I have a first term and I have a common ratio. We said that our common ratio, absolute value of it, had to be less than 1. So in this case, what is our common ratio? X. Therefore, absolute value of x has to be less than 1, which means that x has to be between what two numbers? Negative 1 and possibly 1, right? There's a reason for why this approximation of a power series can approximate this thing, right? Because we know that the sum of an infinite number of terms of a geometric sequence would be the first term over 1 minus the common ratio. It's pretty much amazing that that works out that way. I think really what happens though is we created this language of math, and then because we created it, certain things work out, and then when those things work out, we're like, wow, we're amazing, right? So we kind of set it up ourselves. But it's pretty cool how that works. Now I want to show you on a graphing calculator. Okay, so what I would like to talk about right now is this. When you come up with your common ratio, and you say your common ratio has to be less than 1. In this case, our radius of convergence is equal to 1. There might be scenarios, which we'll see pretty soon here, where our common ratio might be x over 3. Right? We might have something that looks like this, x to the n plus 1 over 3 to the n. Right? Our common ratio in that case would be x over 3. Now, we know that our common ratio always has to be less than 1. So our radius of convergence is no longer 1. What is it? It's going to be 3. Our radius of convergence there would be 3. Okay, so any values between -3 and 3 would now work. All right, so our radius of convergence will change. This thing right here, right, when we solve the inequality or put it out in expanded form, this is called our interval of convergence. Okay, our interval of convergence, and you can write it in either form, either interval notation like such, or in the inequality form that way. Now, what if r equals 1? What test did we normally use if we were like, oh, shoot, we found out, we use what test? The ratio test. We then employ the ratio test if we got an r value of 1, right? So what we're going to eventually do here is we don't really know here. We don't know if this is going to be brackets or parentheses, right? We don't know if it'll be greater than or equal to. We don't know for sure. So we're going to have to test those endpoints eventually using the ratio test. What do you mean? Well, that means I'm going to take this 1 and this -1, and I'm going to go ahead and plug it into the series above for x. And then I'm going to use the ratio test on that new function. Okay, so let's navigate. So here we go. We're jumping into day number 6 on radius and interval of convergence. Let's go ahead and jump right to an example. All right, so if we look at this series right here, this is written in power series form. What can we say that the common ratio would be? I know my first term is 1. What's my common ratio? X over 3 each time, right? Oh, well, that was convenient. So what I've got here is x over 3 must be less than 1. If it's equal to 1, then we got to do ratio test on it. But now I know my radius of convergence is going to be 3, right? Because this implies that the absolute value of x would be less than 3. Therefore, my radius is 3. My interval, at least from what I'm expecting it to be, I don't know. I just know it'll be -3 to 3. I don't know if it'll include those endpoints. I don't know if it'll include those endpoints. All right. Now, an alternative to what we've done here would be to also, instead of identifying it just the way we did, we said x over 3 each time, is you could use the ratio test on the original series, right, which would be n equals 0 to infinity of x to the n over 3 to the n, right? X to the n over 3 to the n. You could do the ratio test on that, but what you're going to find is it's x over 3. Ratio test will lead you to x over 3. Okay, so now let's take this and let's test these endpoints. So let's take what we know, x to the n over 3 to the n, and we're saying that x equals, what, -3, and x equals 3. Okay, well, this is going to be a really dumb one, but okay, that's cool. So let's plug x equals 3 in first. The new series would be negative 3 to the n over 3 to the n. All right, which would be equivalent to negative 1 to the n times 3 to the n over 3 to the n. Would this series be convergent or divergent? Do I even need the ratio test? I don't. Right? Would it be convergent or divergent? It'd be convergent? Well, what about this one then? 3 to the n over 3 to the n. Would that be convergent or divergent? Well, yeah, it'd just be 1, right? What happens if I add 1 all the time for the rest of time? It's going to be 1 for the rest of. Well, you can. You can. What would be the sum from n equals 0 to infinity of 1? Infinity, right? So it's divergent at negative 3. Same thing is going to happen at positive 3. It's also going to be divergent at positive 3. I don't even need the ratio test. So I can say that the interval of convergence would not include its endpoints. Would not include its endpoints. Okay. Maybe made too much out of a simple example, but could you come up with the radius and the interval at this point? Yeah. We're going to learn how to test the endpoints. So let's test the endpoints on something different. Hold on, I want to see one of these future examples up here that I like. Find the radius and interval of convergence of this. What would the first term of this sequence be, or series? 1 times 5 to the 1 times x, right? So I get 5x. What would the second term be? 2 times 5 squared times x squared, right? So that would be 50x squared. Let's go to the third term just to make sure that nothing's getting crazy over here. So then it'd be 3 times 5 cubed times x cubed, which would be 375 x cubed. How could I find the common ratio relatively quickly? Take any term and divide it by what? The term before it. Okay, so although in this case it looks like it's changing each time, isn't it? So it's not as straightforward. So what I'm going to want to do in a case like this is use the ratio test. Let's use the ratio test and you'll see why that makes sense. Okay, let's use the ratio test. So in the last example, it was pretty straightforward. It was like, oh, I can see the difference from one to the next. What does the ratio test say? Take the limit as n goes to infinity of the n plus 1 term over the n term. Okay, I'm going to do the n plus 1 term. Oops. I'm going to do the n plus 1 term times the reciprocal of the other. And actually, I don't want to do that. That would be dumb. Yeah, that'd be dumb. Thanks. Thanks for not scolding me. Over n times 5 to the n times x to the n. Okay, so how can we reduce this? Limit as n goes to infinity of, well, this would be 5 to the n plus 1 over 5 to the n, which would be 5. So I have n plus 1 times 5 times what? Times x over n. What will happen to this as it goes to infinity? Becomes 1. Therefore, my radius of convergence will be 5x. I want my radius of convergence, excuse me, that's not my radius of convergence. That's my common ratio. I want my common ratio to be less than 1 at all times in order to make it converge. So what will x be between? Yeah, negative 1/5 and positive 1/5. Those are the values for x. That is the interval of convergence. The radius of convergence would be 1/5. And the interval of convergence would be x less than 1/5 greater than negative 1/5. Now, do we know if it'd be equal on those points yet? No. Yes. I'm getting a limit of 3x. Right? So as n plus 1 quantity squared over n plus 2 quantity squared goes to infinity, that'll go to 1. And therefore, I get 3x. Therefore, my radius of convergence will be, what is that, 1/3? And my interval of convergence, at least at this point, will be this. I want to show you how to do this. I want to show you that this actually will be an interval of convergence of that. So this is going to be the actual interval of convergence. And here's why. Okay, so I'm going to plug in a negative 1/3 into the original series and a positive 1/3 into the original series. Someone tell me what the original was. Okay, so I'm going to plug in a negative 1/3 for x. All right, so let's plug it in right here. Let's plug in negative 1/3. So I have 3 to the n, negative 1/3 to the n over n plus 1 squared. If I can show that this series will converge, then I can make this statement that we would include that endpoint. How do I determine if an alternating series, right? If an alternating series, this would technically, what's 1/3 times 3? Negative 1, right? So I'd have an alternating series that looks like this. What do I have to do to show that an alternating series converges? I have to do two things. First thing, show that terms are decreasing, right? B sub n plus 1 is less than B sub n. Will that be true? Well, this isn't B sub n because it's alternating, so that would be bouncing back and forth. This shouldn't be a squared, that should be an n. Okay? So what would B sub n be? It would be 1 over, B sub n plus 1 would be 1 over n plus 2 quantity squared. Would that be less than 1 over n plus 1 quantity squared? Yes, because the denominator would be greater in all cases because n is always positive. So we could check off the first thing. All right, what was the second thing? The limit of what? B sub n, 1 over n plus 1 squared. Would that go to 0? Yes, it would. The denominator would go to infinity, therefore that would go to 0. Therefore, this series right here, this series would converge, and because that series would converge, I can say that it would include that endpoint. Let's do a quick version of the second one. What if I plugged in 1/3? How would that change this series right here? What would change? That'd just be 1, right? And wouldn't that be the same as its alternating series then when we just take B sub n? B sub n would now just be what B sub n was before, which is n plus 1 quantity squared, which will satisfy both of these. Okay, so we checked the alternating series convergence by checking its, in this case, we were lucky, but its non-alternating friend, right? 1 over the quantity n plus 1 squared. So we could also say that that would converge. I'm not going to go through the formal part. It would be exactly the same. We would, b sub n is just now equal to the series itself. And so we can include both endpoints. So because we're convergent at the endpoints, we would also include them. Let's stop here and